like the participant numbers are stabilizing. My name is Robert Heinze. I'm the interim department head for the Soil and Water Systems Department here on the Moscow, Idaho campus. I'm filling in for Tim Link today, who is traveling, but I am familiar with the seminar series. I used to run this seminar series for a number of years. With that, David, if you wouldn't mind introducing our speaker today.
Okay, I'm David Hokum. I'm the president of the Idaho chapter of the American Water Resource Association. We've teamed up with IWERI on this seminar series to bring you speakers for the series. Anyways, as you may know, the Idaho Water Resource Board has teamed up with Idaho Power and has developed one of the leading cloud seeding programs in the United States. But Utah has invested a significant amount of money recently to develop their cloud seeding program, and we thought it'd be useful to bring in the Utah perspective on cloud seeding to you. And so it'll be introduced to you by Jonathan Jennings. He's a meteorologist and cloud seeding coordinator for the state of Utah. He has over a decade, I think 13 years of experience operating and managing weather modification programs in Texas, and is now overseeing operations, research, and policy in Utah. Jonathan also previously served as the president of the Weather Modification Association. So with that, Jonathan, go ahead.
All right, thank you, David, and I hope everyone's doing well today. I expected to be in a little bit of a bad mood, considering that the DOGE House Oversight Committee just had their first hearing about a cloud seeding and geoengineering ban, but honestly, it did not go as they expected. I think it backfired on them a little bit, so I'm in a much better mood than I expected to be, but very glad to be here. I want to give you a little bit more of a background about myself. I was actually born and raised in Western Pennsylvania. Graduated from Penn West, California in 2008 with a degree in meteorology. There I served as president of the Southwestern Pennsylvania chapter of the American Meteorological Society. I then took off and went west to Texas, where I managed and ran operations for convective cloud seeding operations. So this is during the warm season. I'm licensed by the state of Texas to hold the certification to do these types of operations. Towards the latter half of my career in Texas, I became involved in the Weather Modification Association, where I was on the executive board and then entrusted with becoming the president of the WMA. I'm also certified as an operator and manager by the WMA. And then most recently, of course, here I am in Salt Lake City, where I'm the meteorologist cloud seeding program manager for the Division of Water Resources. Before we get into kind of what cloud seeding is and what it's not, I wanted to make sure I bring this up. This is from a 2003 report by the National Academy of Sciences called Critical Issues in Weather Modification Research. And something I like to bring to everybody I speak to is this quote: "The committee emphasizes that weather modification should be viewed as a fundamental and legitimate element of the atmospheric science." Cloud seeding, weather modification sometimes get the reputation that it's snake oil and we're just a bunch of cowboys up here doing cloud seeding, trying to make it rain. When in reality, it's actually a strong element of the atmospheric science, and especially when it comes to the understanding of cloud physics and the microphysical processes that's occurring within our clouds. A lot of our current forecast models that we use today, the microphysical schemes embedded in those models come from the research that has been conducted over the past 40 to 50 years from cloud seeding. So I just like to make sure that people understand this is a true science, something that's been around for a long time, and something that's widely accepted amongst our peers in the atmospheric sciences. Before we talk about what cloud seeding is, let's talk about what it is not. And this is kind of the frustration behind what I just witnessed with the DOGE Oversight Committee. And that's the idea that jet contrails are some type of weather modification tool, whether it's for kind of the more streamlined idea of trying to block solar radiation to cool the planet down, or in more extreme cases, something like mind control, poisoning, or the release of the COVID vaccine. But the EPA recently came out and made sure that they said that chemtrails is a shortening of the term chemical trails, And it is a term that some people use to inaccurately claim that contrails resulting from routine air traffic are actually intentional release of dangerous chemicals. Now, geoengineering, something like that, it's theorized that it could have an impact, but overall, the solar radiation is able to make it through these higher cirrus clouds or clouds that are developed in primarily ice crystals. They make it through with no problem, but the radiation forcing back into the atmosphere or back into space, that actually acts as a blanket and can have a net heating effect. So scientifically, like this idea of releasing something like this, like these chemtrails, actually would have a net heating effect and doesn't really test or last against physics. So this is certainly not us. Instead, this is kind of what your more operational plane would look like in terms of convective cloud seeding. So this is in Texas, where we're flying at the base of an already precipitating cloud. So cloud seeding is the act of introducing favorable nuclei into a precipitating cloud to promote cloud droplet growth and ice nucleation. And we really focus on localized effects. We like to not use the term cloud seeding as much anymore because it does get misrepresented with the idea of geoengineering. So I've been using rain enhancement more or precipitation management to make sure that it's very defined about what we are talking about. So why do we do this in the Mountain West? Well, several reasons. First, it's a very affordable means of new water production. We have a lot of supercooled liquid water in our clouds, and I'll talk about why that's important later. We have a lot of aerosols and dust. A lot of the Mountain West states have great mountain areas, but then are surrounded by adjacent plains that are sometimes in desert areas where you don't have as much precipitation. So you could get a lot of dust and aerosols that could get suspended into the atmosphere. And that could have really strong negative effects on our clouds. And in some cases, it could have a positive effect. So we have to understand that a lot better. And then we all know water demand is going through the roof. And then when it comes to SWE, so for those of you who may not know, SWE is the snow water equivalent in our snowpack. We have like a boom or bust cycle. And what I mean by that is over the last 30 years, the way we measure our SWE is by the percent of normal compared to historic average. And on April 1st, give or take a few days, that's when we generally see the peak of our snowpack. Those last 30 years, have we only seen 3 years fall within 5% of normal. So we're either having a really wet year or we're having a really dry year. And we also need to incorporate the soil moisture. Soil moisture plays a very important part of runoff efficiency. So these are all reasons why we need to be cloud seeding and trying to produce as much water as we can in our winter snowpack. There's two types of seeding modes that we focus on, and we're going to focus more on glaciogenic seeding, which happens in here in Utah and also happens in Idaho. We don't see hygroscopic seeding taking place in winter programs. That's more for the summer convective programs. But what glaciogenic seeding is doing, it's that ice nucleation. We're trying to turn super cold liquid water into ice crystals. And why that's important is we have a lot of supercooled liquid water in our clouds that doesn't have enough of a surface area for freezing to occur. So they stay stagnant in the atmosphere. And because these droplets are so small, when they collide and coalesce with one another, or collide, they fail to coalesce one another. The surface tension is so low, they just bounce off of each other. So the process of droplet growth through the warm rain process, collision and coalescence, is not efficient. It's just not happening. Silver iodide, meanwhile, is structurally very similar to an ice crystal. So when introduced into a cloud with supercooled liquid water, you're actually going to get freezing to occur much more rapidly. And the process of droplet growth through accretion is way more efficient than the warm rain process. So once that supercooled water starts turning into ice, they start colliding with other supercooled droplets and grab onto that. And then the two ice crystals will hit each other and they'll fracture and spread apart. And that's when the secondary ice process takes place. And you're just now naturally seeding the entire cloud. And the reason we have so much supercooled liquid water is because of how fast the updrafts are occurring, or the orographic lift is occurring in our mountain ranges. There's not enough time for that collision and coalescence process to occur. So everything just gets suspended and all that supercooled liquid water is just sitting there trying to figure out a way to precipitate out as snow. Silver iodide can be a bit of a concerning agent because you hear the word silver. It's a solid metal. We'll talk about a little bit why it's not concerning, but again, structurally, it resembles an ice crystal, and it's effective at temperatures around -5 to about -20. Anything warmer than -5, you're probably not going to see the nucleation process take place. And then anything colder than -20, ice is already probably happening naturally. It's just too cold. Everything's just falling, turning into ice immediately. So there's no need to see clouds when it's that cold. Meanwhile, we do have a program in central Utah, and research is ongoing in the Camas Prairie of Idaho using liquid propane. So when you evaporate liquid propane, it creates a burst of evaporative cooling, and it freezes everything from -40 all the way up to about 0 degrees Celsius. Now, there's some limitation to this. It must occur in the cloud, so these generators have to be based at like 8,500 to 9,000 feet or higher. And the dispersion isn't going to impact as large of an area as, say, the silver iodide generators. So these are really good tools for really narrow canyons or possibly ski resorts. But we still have a lot to learn about liquid propane, the effects of it. And that's why the National Center for Atmospheric Research is doing this research in Idaho. When it comes to hygroscopic seeding, we use calcium chloride. That's essentially table salt. It has a 65% deliquescence relative humidity. So when you introduce these salts into supersaturated environments, saturation occurs immediately, and you get these really large rain droplets in the warm cloud base that just become heavy enough and fall as precipitation. But that method's not used in Utah or in Idaho. So let's talk about the environmental considerations, because silver iodide could be scary to some folks, but really, silver and iodide have a very strong electronegativity, and this results in a stable and very strong covalent bond. So this allows it to be insoluble in water, so it stays in the solid phase, and that's really good for two reasons. One, we're introducing this as a seeding agent into a supersaturated environment already, and we want the particle to survive the non-supercooled water, or at least the water that's warmer than -5. We want it to survive that and then make it to those droplets and interact with the supercooled water. And it does that because it's insoluble in water. But also, when it gets on the ground, it stays insoluble in water and has very limited impacts in our water supply, our soil, amongst other things. So a really good study done in 2011 out of California and a company called Cardno-Entrix. They were measuring the quality or the quantity of silver that actually comes off the silver iodide when in water, and the maximum is 0.984 micrograms per liter. So it doesn't matter how much silver iodide you put in the water, the maximum concentration of the silver ion coming off is 0.984 micrograms per liter. This is 6 times below the natural levels, the natural background levels of silver. And the EPA drinking level standard is 100 micrograms per liter. So we're well below that. Meanwhile, to start having impacts on aquatic life, you need to be anywhere in 2 to 7 microgram per liter range. And then terrestrial life is like 10 to 10,000 micrograms per liter. So we're having no effect in our water supply. Now, when it comes to silver iodide on soils, it's going to end up turning into what's called silver nitrate, and that's completely insoluble, and it just ends up being part of our background material. Soil erosion takes place, and the way we try to measure how much of the silver is being released out of this, we have to do it in the parts per trillion. And right now, there's only 2 labs that I know of that can do that, and that's the University of Wisconsin and Boise State. So I talked about the environmental studies in California. Idaho Power's done some studies. The long-term programs in Utah, we've had no silver beyond our background levels. We've been doing cloud seeding since 1974 here, so we have a 50-year track record. San Angelo, Texas, they've been doing cloud seeding since 1995. They test their water annually and have no issue with silver in it. But still, part of our big research plan is to incorporate an extensive environmental impact review to make sure that our findings are consistent with previous studies as well. So let's talk more specifically about the Utah program. So all these different colors on the map are the target areas that we work in. And these are all higher terrain areas. So everything's about 6,000 to 7,000 feet or higher. And we have been traditionally a ground-based program. So we put ground-based generators along the foothills, mid-elevations, and we rely on winds that are somewhat, or at least somewhat perpendicular to our mountain ranges. And that spreads or disperses the material for us. So over the past 50 years, we've been using manual generators where an operator or landowner would have to actually go outside and turn the generator on themselves. But with the recent increase in funding, we've been able to modernize our programs and invest in a state-of-the-art remotely operated generator. So now our meteorologists can work in the comforts of their office and just turn them on remotely. And this allowed us to put some of the generators in harder to reach areas that have greater impact. So it's been a plus plus. All of our generators on November 1st of this year will be remote. We've also invested in a state-of-the-art software program that we're calling Stratus. And there's going to be two versions. One is going to be an operational version where we can actually turn on generators. We could do modeling efforts to see where the dispersion is going to take place, overlay radar, overlay satellite data, everything a geeky meteorologist will want. But we're also going to have a stakeholder version of this where our sponsors, state program partners can pull up the software and they can see exactly what generators are turned on, how long they've been running for, and then generate reports based on interest. If they want to see what's been happening in the Colorado River Basin, they can ask, well, how much generator runtime is taking place in this basin? And it'll produce that result for you. So we're trying to increase our transparency and increase the trust with the public in terms of our operations. Over the last 3 years, we did dabble in aircraft a little bit. We've had some challenges with that, whether those were self-induced in terms of aircraft choice, not hiring maybe the more qualified pilots. But overall, the cost was just too high, and we decided to take some of those funds and look at aerial drones. So last year, we actually funded the first experimental drone program in the Cache Valley of Utah, which is just near Utah State University. And we survived in icing conditions for over a half hour. So we're looking at this as a more cost-effective solution in the long term. We also have more rapid deployment. There's times where aircraft can't take off because they just didn't plow the runway for some reason. These are at your smaller airports. And also precise targeting. We could be very precise with the targeting and go in those areas where supercool liquid water is most ideal. So here's a picture of one of our generators. Again, you have to rely on the orographic lift to transport the material. And because we are using silver iodide, we have to have those temperature ranges that we spoke about already. You have to have favorable liquid water content. You want to make sure you have no blocking flow. And then we also look at stability. Stability is a big issue here. So if it's too cold and we get a winter inversion that kind of traps in a lot of the air, the dispersion is not going to take place because you're too stable. Instead, that's when we release the drones. We get the drones above that stable layer. We get a high split model at those elevations, figure out where the dispersion is going to take place, and then we can start seeding above that stable layer. So the traditional aircraft use these pyrotechnic burn-in-place flares. So these flares could burn anywhere from 45 seconds to about 2 to 3 minutes. The seedability is still about the same. You have to have appropriate liquid water available. You have to have the right temperatures. And then no icing conditions. That's kind of tough because most pilots are trained to stay out of icing conditions. But that's what we're doing. We're targeting the supercool liquid water. So in order for us to be most effective, we have to be flying in those icing conditions, or now we could fly just above the cloud and release what's called ejectable flares that shoot down into the cloud and burn. But we just found that the ability to seed for long durations, like in a convective program, those operations are anywhere from an hour and a half to 3 hours. In a winter program, operations could be 12 to 18 to 24 hours, if not longer, depending on the storm. It's just really hard to keep pilots airborne that long, and they get grumpy after about 3 or 4 hours, and for good reason. It's really cold up there. Chances are they don't have oxygen. We're flying about 13,000 feet. So we just found that this isn't working too well, and instead, this is a picture of some of the drones. So in this picture, the drones look kind of small, but they're actually 6 feet wide. They have a 6-foot wingspan. They weigh about 49 pounds, and they could carry about 100 grams of silver iodide material. And instead of releasing a pyrotechnic flare, we're actually releasing just a pure powder form of silver iodide. So no fillers, nothing in there that we need to do to increase the burn rate. But that's up. These are the drones, and we're going to have about 32 of them deployed in the Bear River Basin this upcoming winter. So I think the biggest challenge in our field is determining the evaluation. How successful are we? And with winter programs, we've done target and control evaluations of highly correlated snow tell sites. So these are the sites that measure that snow water equivalent for us. And using a linear regression method for our Southern and Central program, we were able to show about a 6 to 12% increase in SWE. And a 2018 study out of the Division of Water Resources showed that translates to roughly 200,000 acre-feet of additional water supply. That's a good amount of water, but I still think that this evaluation might be undershooting the impacts a little bit. But overall, our program and other programs nearby who use a similar target control evaluation method, but sometimes a little bit different, everybody's showing a consistent 10 to 15% increase. And that's mirrored by the convective programs as well, especially those in Texas. But of course, there's challenges with this. First, we're looking at point observations. So we're trying to represent a very large area based on one point. We have snow redistribution issues that could be impacting what we're looking at. And also, not all increases are the same. If you increase snowpack by 10% in January, that's great. But if you do it in April, especially if you have a dirty snowpack that's able to absorb the sun rays and increase heat and kind of initiate runoff a little bit sooner, if you're able to create a more fresh snowpack that has a higher albedo, you could delay runoff, which increases runoff efficiency. The other big issue that we're having is we're expanding so many of our target areas, and this isn't just Utah, it's Colorado, it's Wyoming, it's Idaho, to where some of our control sites that we've used historically are now part of operational programs. And then some programs have outlasted climatic periods like this here. The Southern and Central program has been ongoing since 1974. And then I think one of the bigger issues too is we have limited instrumentation. So radar coverage is a big issue, primarily because the radar blockage. But down here in Utah, we have 2 radars in Cedar City and then the other in Grand Junction, Colorado. They're sited at 11,000 feet elevation. Our winter storms rarely are that deep. They're pretty shallow storms, so we don't see a lot of our winter storms on radar. How do we overcome some of these challenges? Well, fortunately, the National Center for Atmospheric Research have developed the WRF weather model. And what this does, it simulates the dispersion of our ground-based generators, and it shows where those silver iodide seeding particles interact with supercooled liquid water in the cloud, and it creates a snowpack. And then that data gets ingested into the WRF hydro model, and then we can start to get stream flow estimates. So this is kind of a more expensive way of evaluating a program. So it's not something that we're going to be able to do annually, but we are doing a big research program that involves the WRF hydro and WRF weather model. But of course, you need to calibrate these models to work in your areas, and that's part of our research as well. And by creating ensembles and looking at a really bad, really dry year, and then looking at a really good wet year, we could create a range of expectation. We know we're not going to be able to create a volume of water and be 100% certain about it. But if we know what the range is, then that gives us a range of our return of investment, which is extremely important to our legislators who fund these programs. Another way we can overcome these challenges is by taking care of the instrumentation issue that we have. There's a company out of Kentucky called ClimateVision, and they're installing gap-filling X-band radars all across the western or eastern U.S. They're trying to expand into the Mountain West. So if we could put these gap-filling radars in the proper areas, then we're able to understand our precipitation patterns a lot better. And they actually have a CRADA, an agreement, cooperative agreement with the National Severe Storms Laboratory, where all of their data gets ingested into MRMS. So that's multi-brain, multi-sensor. And that'll really help with things like the wharf hydro and the national water model, and being able to determine the accuracy of what's happening, and really good for water supply forecasting. We're actually expanding our K-band vertically pointed radars. We're going to have about 15 of those across the state of Utah. The Southern Nevada Water Authority received a grant from the USBR. They passed those funds on to the upper Colorado River Basin states. So we purchased radiometers, which scan and look at liquid water in the cloud. And then salometers are another tool that we use to look at cloud base. So here's a picture of the radiometer install that we put in Logan, Utah. And again, this is scanning the sky. It's going to look at the liquid water content that's in the skies, but also have a temperature profile. And then that'll give us a really good idea of where that supercooled liquid water is. It allows for better targeting practices, which makes things just much more efficient for our operators. So let's talk about Snowscape. Snowscape's a big research program that we're putting on this winter. Atmospheric scientists love their acronyms. So like the Idaho program was called SNOWY, and we're kind of piggybacking off of that program in Idaho. But seeded and natural orographic winter storms, catchment processes, and evaluations. So very, very excited to have the National Center for Atmospheric Research leading this. We have a huge group from the University of Utah involved, including Jim Steenberg, who's very well known as a mountain meteorology god. We have Gannett Haller. She's really good with aerosols. Mackenzie Skiles and Paul Brooks, who are really good with snowpack hydrology. Then we're getting support from the Utah Climate Center, who does a lot of our modeling. Heritage Environmental and the University of Wisconsin will be doing our environmental sampling program. And then our contractor Rainmaker will be doing a lot of the operational work. And what Snowscape is, it's a big field campaign where we're creating a transect of high-resolution instrumentation data from Antelope Island Causeway, which is kind of those further west yellow dots. And then we're transecting across the Snow Basin ski area, and then extending further to the northeast across Powder Mountain ski area, Huntsville. And what we're doing is collecting all this data: precipitation, radiometer, aerosol, snowpack hydrology, and all that data is going to get sent to calibrate the WRF weather mod and WRF hydro model, so we have better evaluation tools with the modeling. But we're also hoping to see a physical validation, because we are going to be bringing 2 mobile X-band radars that should be able to see a seeding signature while we do the cloud seeding operations. So we're doing a modeling evaluation, but we're also going to look at doing physical evaluations, and Utah State will help us with that. We're also going to use NCAR to help with program optimization. Did we make mistakes with any of our flight tracks for the drones? Maybe we put some of the generators in bad locations. They're going to help us determine that, which is really exciting. And then, of course, we'll be doing the environmental study. So what's ahead for Utah in 2026? I mentioned all of our generators are going to be remotely operated moving forward. We're going to get better dispersion rates. We're going to impact larger areas, and we're going to have much better stakeholder engagement. We have this very large Bear River Basin program, which is co-funded with the state of Idaho, which we're really excited about. The primary goal of this is to continue to look at the efficacy of drones for cloud seeding operations. Like I said, last year's operations in Utah were more experimental, just trying to figure out, will the drones survive in these icing conditions? And we proved that, yes, they can. Now we're trying to figure out, will the powder version of silver iodide nucleate at the -5 level? And can we actually survive in icing conditions while seeding? So it's a really exciting time for the Bear River program. And then we're also hoping to build a stronger Colorado River Basin program. I'm shocked I've gone through this presentation this long without mentioning the Great Salt Lake. We obviously have a lot of challenges on our hands here in Utah when it comes to providing water for our water right users. But then we also have to make sure that enough water is provided to a terminal lake, because if the Great Salt Lake goes dry, there's many things that can go wrong. One, the ecology impacts would be just huge. And two, we have arsenic dust embedded in our lake bed, and that gets exposed. And on those windy spring and fall days, all that dust gets blown into our valleys where we all live. So keeping water in the Great Salt Lake is extremely important. But then we can't forget about what's happening in our backyard too with the Colorado River. So we've kind of ignored the expansion and modernization of the Colorado portion of our program, the Colorado River Basin portion. So this year we're really making that a priority and strengthening our program there. So I probably went a little faster, but I hope I get a lot of questions. But a few concluding remarks. Something I want to make sure is that people understand that this has been going on for decades, and it's widely considered a tool for water resource management. I want to make sure that it's understood that it's a long-term water management strategy. We are not going to fill the Great Salt Lake with cloud seeding. It's just one of those tools on your tool belt to deal with the situation that we have at our hands. Beyond Utah, Idaho, Colorado, Wyoming, Nevada, Texas, North Dakota, New Mexico, Arizona, and California all conduct some form of cloud seeding. I do believe that we're going to see programs come online in Oregon, Washington State, and Montana in the coming year. And then when you look at the evaluations that we have currently, a 10 to 15% increase, that produces an acre foot of water for $10 or less. Assuming we've made no additional water with our increased budget, we're producing an acre foot of water for about $27. And our budget went from $350,000 a year to $5 million a year. So we saw a significant increase in our budget. We also received a one-time fund of $12 million to help us with the research needs and the modernization of our equipment. Cloud seeding is safe, it's effective, it has no butterfly effect due to the abundant moisture in clouds. One of the biggest questions we often get is, are you robbing Peter to pay Paul? Well, when you look at a cloud system, only 9% of the total moisture in a cloud is precipitating. And if cloud seeding is effective at the 10% range, then that turns into 9.9%. So we're having a minimal impact on the overall moisture content of a cloud. In fact, the phase change from a supercooled liquid water droplet to an ice crystal releases heat in the cloud. That latent heat that's released, just like a hot air balloon, allows clouds to expand, grow, and last longer. So we're actually seeing extra area benefits extending beyond our program's target areas. And then I think most important to make people understand is cloud seeding is certainly not chemtrails. Very, very different things. So I hope you found this presentation informative, and I would love to open up the floor to questions.
Yes, thank you so much. Wonderful presentation. If you do have a question, if you would like to raise your hand or put the question in the chat.
I have a question. I don't know how to raise his hand.
It looks like David sent something in the chat for more details on the evaluation using WRF Weather Mod. Yeah, WRF Weather Mod was designed in 2013 by the National Center for Atmospheric Research, and over the last 10 plus years has gone through extensive updates. It's still a model. We realize and understand that. And it's at a 3-kilometer grid, so it's not perfect, but by being able to ingest that data into the WRF Hydro, we're going to be able to get volumes out of it. What goes into the WRF Weather model is the location of our generators, so they know exactly where our generators are. And then we also are putting in the particle size and particle size distribution of the seeding material that's coming out of our generators. And that's very important because that's kind of the driver of whether or not we're going to be effective. Beyond that, I would have to defer to the NCAR team to give us more understanding of the WRF Weather Mod. And David, I can certainly get you connected with them.
Thank you for the presentation. Can you guys hear us here in the Water Center?
Yes.
Awesome. I'm curious, what is the current understanding about the uncertainty ranges coming out of those models?
Oh, that's a really good question. You know, I've heard NCAR talk about anywhere from like a 5 to 10% The WRF model itself, without any input from the weather model perspective, the WRF model itself has a tendency to produce less precipitation than observed. But those are better details, I think, that I need to learn from NCAR. But that's a great question. I don't have a perfect answer for that one. Sorry.
Thank you. Appreciate it.
Rebecca has her hand raised.
Hi, yes. I'm currently taking a drone class, so it's pretty exciting to hear about the additional ways drones can be used, like for cloud seeding. I was wondering, for the piloted aircraft, do your pilots need additional licensing or testing to maintain their compliance, since you guys have to operate under like unique regulatory conditions, like flying through the icing environment?
Yeah, so the pilots for the traditional aircraft program are obviously they need to have a commercial license so they could be paid. They have to be instrument certified. So we have to fly in what's called instrument flight rules, or IFR. So that is pretty standard for a lot of these pilots. The biggest issue is trying to find people that are willing to do that in supercool liquid water. But in terms of additional criteria that they have to meet, that's not part of it. Now, the Weather Modification Association does have a certification for pilots, and we're hoping if we do bring back the airplane program that we do have certified pilots that have the required certification and expertise to fly in these conditions.
Thank you.
Conrad added another question to the chat, and he's asking, is there ongoing work on looking into more efficient nucleator materials, for example, biological ions like snowmax or something similar?
There's a lot of research happening in biological ions right now. The companies that are doing the work are privately funded, or like venture backed. And in order for me to understand exactly what they're doing, I have to sign a non-disclosure agreement. My DWR will not let me do that. So I don't know the details of what they're looking at, but I do know that some of the biologicals that they're looking at do nucleate around -2. There's a company called Flagship Pioneering who's kind of leading that effort. And their company actually is one of the companies that developed, I think, Moderna or Pfizer, one of those pharmaceuticals. So they're backed with billions of dollars. So I think they're going to end up being successful one day.
Well, small funny story, because they patent our bioelectric ions. We are the ones that provide them the technology. That's why I was wondering, because the knowledge is here and not through them. And I was just wondering why we don't use it in the state then, which is kind of funny.
Yeah, we don't know about it yet. Let us know about what you're doing, and we'll shoot me an email, please.
Yeah, absolutely.
Good. Ethan added another question to the chat, and he's asking, what are the biggest challenges in evaluating success in Utah's mountainous terrain?
The biggest challenge is natural variability. The thinking of what would have happened had you not seeded. And that question is extremely hard to do or to answer. So the biggest challenge is just that, but also coverage. Again, our snow-tell sites are a very, very small representation of the entire mountain range. And though we have decent coverage of snow-tell sites, it's still not perfect. So that's where something like a gap radar could help us with. There's a private company out of Colorado that does radar transitions to SWE. And being able to look at an entire mountain range and decipher how much water is actually in that mountain range would help us a lot better. So instrumentation challenges, and then just how aggressive the terrain can be, and these very micro scale, smaller weather events that could drop, feet and feet of snow in very small areas. So a lot of challenges on our hand when it comes to evaluations.
There's another question from Anna, and she's asking, what was the transition like from Texas cloud seeding to Utah, and the difference in attitudes for the stakeholders?
That's a great question. Texas has very little to no legislative support for cloud seeding. The state funding went away, I think, in 2003. And since then, the programs in Texas have been primarily funded at the local level, so water districts. And these water districts and the farmers and ranchers are extremely supportive of the program. Here in Utah, we have great legislative support. Our water districts also support it, and our local, like farmers and ranchers, generally support it. But in a bigger city like Salt Lake City, we do get a lot of pushback, and I think it's because there's so much misunderstanding of what cloud seeding is and what it's not. Our social media team here at Water Resources did do a post about cloud seeding last February, and it went viral. 5,000 comments. Things about chemtrails, things about poison, things about God. Are we playing God? And my response to that is we plow fields to farm, we divert water, we create reservoirs. We're always doing some form of playing God. But I think locally we could do better with education, but I think there's a little bit of fear about what happened with that post because many of our staff did receive death threats during that period. So we've been a little quiet since then.
Wow. Perfect. Another question in the chat from Tao. He's asking, thank you for the interesting talk. I'm just curious, what is the approximate ratio of cost to benefits?
From the pre-2023 budget, we were somewhere in the $5 to $10 range. So that was with a $350,000 budget. Assuming we made no additional water, but now we have a $5 million budget, we're showing about $27 per acre foot. Now, the state of Wyoming, they did a similar weather-mod wharf hydro evaluation. And there they were showing it close to about $100 per acre foot, so a little bit more. I think Utah's program is a lot more robust, so I'm hoping to see numbers around that $27 to $50 range, which is still pretty cheap when it comes to water.
Bruce Savage, if you want to unmute yourself and ask your question.
Sure. Oh, apologize, my camera is off there. So, Jonathan, I appreciate the presentation. I really enjoyed that. A lot of good information. You talked a little bit about instrumentation. I'm kind of pulling back from my memory a little bit because this is really in my area, but I believe there was a person at the University of Washington, he's since retired, Ragno and Hobbs, and he put out a paper. They talked about reviewing the Colorado River Basin back in the 70s or 80s, I believe. And if I understood it correctly, I just kind of skimmed it. Once again, it's not really my area. But what I took away from it, they thought that the cloud seeding was over predicting the amount because the instrumentation wasn't good enough to collect enough data to say what the baseline is. Mm-hmm. Is that a fair representation? Or how would you respond to that?
But yeah, definitely a fair representation. In fact, a lot of the research that was done back in the 60s and 70s, they were just so many constraints with instrumentation and technology. So I think that's why the federal government started to back away, is because they were unable to show that physical validation. The statistics were showing good things, but the physical validation was lacking. And really, I think that maintained up until 2017. So the study in Idaho, Snowy, that was co-produced, I think, with Idaho Power as well as the Department of Water Resources. The study that came out of that was using a very sensitive X-band radar. And they were able to do a flight track, just going back and forth, north and south, same exact area. And they were finding zigzags because obviously clouds are going to move from west to east. So they were finding these zigzag patterns, very unnatural zigzag patterns of precipitation. And that's when we were all like, wow, there's the physical validation that's been missing. Now, our S-band radars that we have today, like the National Weather Service NextRad radars, they're not sensitive enough to pick that up. And that's why we need much better instrumentation in order to continue to validate cloud seeding efforts. But that is going to be extremely expensive just for the cloud seeding program. So that's why the modeling is coming in. It's easier to model on a larger scale than it is to put all these radars everywhere. But I do think here in Utah, at least with the Olympics coming up, the X-band radars are going to be a big priority. And I do believe we're going to get to a point where we have decent enough coverage to continue evaluating programs similar to what Snowy did in 2017.
Okay, thank you.
Sarah, questions from Pocatello.
Hi, yeah, thanks so much, Jonathan. I really appreciated the talk. I was curious if you've seen a change in the conditions under which cloud seeding is, assumed to be operational and really effective. Are you seeing changes in that, either in space or in time?
Oh yeah. So we're obviously at the mercy of Mother Nature. Mother Nature has to provide for us in order to be effective. And one of the biggest changes we're seeing is in our lower elevations. We're finding that the seedability of our lower elevations, 7,000 feet and below, are less frequent. And I think we're seeing that that -5 degrees Celsius range is getting a little bit higher up in our mountain ranges. So where snowpack at our high elevations hasn't changed much in the last 20 to 30 years, our lower elevation sites are completely changing. In fact, Salt Lake City, at the airport, we were over 30 inches below normal in our snowfall this year, and that's not out of normal for the last decade. So we've seen our average snowfall over the course of the last 3 decades be reduced by 10 inches per decade. So yeah, we're definitely seeing some changes in the patterns and the seedability of our lower elevation sites.
And do you have the data to show sort of a similar increase in seedability at higher elevations if there's really a shift in kind of the primary elevation bands that are eligible?
Our higher elevation sites haven't really been too active because we were unable to get too many generators up there. It's only been since we've been able to get these remote generators because people don't live at 9,000 feet, at least in Utah. So it's really hard to get people to go out there and turn those generators on. So generally the generators would be down. So that data would probably be a little skewed and maybe not representation of actually what's going on. But in terms of snowpack, not much has changed in our higher elevation sites.
And are those higher elevations something that's a focus of the WRF Hydro and WRF Weather Mod that you're looking at on the modeling side?
Absolutely. Absolutely. Yeah. So the reason we're focused on the area that we are is we just implemented our first fully remote program that we call the East Shore program. And some of those sites are very high up. So we want to understand the spillover effect of what's happening on our mountain ranges.
Thanks so much. I appreciate the multiple questions there. It looks like there's another one.
Yes, there's another question in the chat from Jessie Anderson, and she's wondering why the Bear River Basin was picked, and you can talk a little bit about the process with the drones.
Yeah, so 60% of the inflows that go into the Great Salt Lake are generated from the Bear River. And we felt that the Bear River obviously offered a lot in terms of water production for the Great Salt Lake, but also provided an opportunity to look at cloud seeding from a basin perspective as opposed to a political boundary perspective. And too many times are we missing opportunities in the Bear River because we can't operate in Idaho or we can't operate in Wyoming. So this was really a two goals we were trying to hit is one, produce more water for the Great Salt Lake, but also two, provide a template for other states on how we could work together to address these water resources needs. So we're really excited that we were able to come to an agreement with Idaho to do this. What it's going to look like in terms of the drone teams. So 32 drones, we're going to have 16 different teams. They're going to be somewhat mobile. We have just multiple landowners that are very supportive of the mission, that are providing land access to us when those conditions are right. We'll have a meteorologist in-house that's looking at everything, and they'll be communicating with a team of what we call forward deployed engineers who will be using the drone. So we will have drone teams on site, and they're going to go where the weather tells them to go. And then each team will have 4 total drones, and they will rotate. So the drones will stay airborne for about 45 minutes. When that one is done dispersing material, the meteorologist will let them know whether to do a second run. They'll send the second drone up when they bring the first one down, replace the battery, refill the solution, and just keep going until the conditions are no longer there. So that's how the drone deployment will work. We had a proposal to incorporate ground-based seeding in the Bear in Idaho, but the Board of Water Resources wanted to first look at the efficacy of drones before investing more into the ground program as well.
Very good. We have time for one more question.
Those were some awesome questions, y'all. Thank you so much.
Indeed. It seems like we've exhausted the question. We've all learned a lot. So let's give our speaker a hand for a fantastic